Hey everybody, welcome. Hopefully you are here to see me. My name is Ian Cooper, talk about event-driven collaboration. What I mean by that is when we have an event-driven architecture, how do we get different, say, microservices in that architecture to collaborate with each other to give basically functionality. I have tended to notice over time, teaching kind of a messaging workshop and working at various companies, that one of the key problems people run into with an event-driven architecture is trying to understand how I get all these different microservices to collaborate to solve a problem. So that's what this talk is about. That's just some information about me. It says two things to you. One, that I'm old, and the other, essentially, that I currently don't work for any kind of consultancy. I have nothing to sell you apart from just share my experience. The point I always draw out, most of all, is the one at the very bottom of the deck. I encourage you all to get up and speak. It can be intimidating to look at speakers and imagine that we are all very smart people. I hang out in the speaker room with a lot of them, and they, like me, are no smarter than you, I promise. You're just the same. A lot of us are just lucky enough to have been given the opportunity to speak at user groups or other events and built confidence, which is the main thing, which lets us come and stand in front of you guys. But I am no smarter than any of you, I promise. So if I can get this stuff, so can you. How many .NET devs in the room? Okay. Any Python devs? Okay. So I work on an open source library called Brighter. Brighter is a C# messaging library. It provides an equivalent to, say, mass transit or N-service bus. We also have a Python version called Brightside, which interrupts with it. And we also support the functionality of something like Mediator. So if you're interested in getting messaging working in a .NET application or a Python application, please do check us out. We are hopefully friendly and always open to people who want to work on open source projects, particularly for the first time. So please do come along. We've got lots of nice new open issues for people to start work on, and we try and help out as much as possible on our Gitter channel. So we have a Gitter channel that's advertised on the GitHub page, and we'll try and help if we can. All right, enough preamble. What are we going to talk about? So we'll start talking a little bit about an idea from a guy called Pat Helland, from a white paper called Data on the Inside versus Data on the Outside. We will talk a little bit about this notion of how this applies in service-oriented architectures and microservices. We'll then look at requests versus event-driven architectures, and we'll have a brief kind of understanding of what's one of the key advantages that event-driven architectures promise you over request-driven architectures. We'll ask why that can be hard to obtain unless you know some key patterns that you're going to want to apply to preserve those benefits. In pipelines and reference data, we'll talk about those patterns and how you apply them. In correctness, we'll show you some of the things you need to understand to make those patterns work correctly, hence the name. And in compositions and conversations, there's a few additional bits that are helpful to understand once you have an event-driven architecture that are not necessarily related to the main thrust of the rest of the talk. All right, so let's talk about data on the outside versus data on the inside. So I'm kind of, I guess, unfortunate or lucky enough to have begun my kind of career towards architecture when we had service-oriented architecture as a thing. And Don Box, who worked at Microsoft on COM, is probably one of the fathers of SOA. And he came up with what we call the 4 tenets of service-oriented architecture, which are on this deck, and we're going to talk about in a second. Now, you probably will think, I build microservices. SOA is yesterday. I don't care about SOA. There is pretty much a direct line between SOA and microservices. Microservices can be just seen as a modern evolution from things that we have learned. So there's a ThoughtWorks, ex-ThoughtWorks architect now works for Neo4j called Jim Weber. And Jim Weber basically looked at the state of SOA. So we started with web services, SOAP. Don Box also was behind WCF. Started with that model, and people had found over time that led to a request-driven architecture, which we can talk about later, and had problems. People created SOA2, which basically worked with events. We'll show you how you do that. But they got kind of captured, and they got captured by vendors. Vendors, lovely people, obviously, and they decided that they wanted their slice of effectively this architecture. They wanted to make some money from it. So they created a thing called the Enterprise Service Bus. The idea was that all of your communication should go through an Enterprise Service Bus, will help you with workflows, will help you with mapping between different message formats in different systems. BizTalk is an example, really, of an Enterprise Service Bus from Microsoft. And the problem with those ESBs was that they were centralized components, quite often looked after by centralized teams in your organization, where you had to fill in, if you worked in large enterprises, forms in triplicate to get access. And people shoveled a lot of the business logic into this centralized component rather than leaving it in the microservices. And Jim came up with an idea that he called Guerrilla Microservices, or Guerrilla SOA rather. And Guerrilla SOA said, what you really want is just to have your microservices, and you want to use something simple. You can deploy yourself, like have HTTP calls between the services, or essentially have a lightweight broker like Rabbit. And when Martin Fowler and James Lewis defined their microservices concept, they picked on some of these ideas when they built their definition that you can find on Martin's Blicky. And that one was basically repeated as smart endpoints dumb pipes. So they really evolved a lot of those ideas and brought in some ideas from DevOps and DDD that were also emerging at the time to be kind of, what is the current state of understanding? Microservices, the term itself, comes from a guy called Fred George. Fred George is also famous for program anarchy. Some of you may like program anarchy. It says that the developers should be in charge. Nobody else really knows anything. It should all be about software developers. Sort of us just working directly with the customers. We're going to fire all the product managers, they know nothing. We're going to fire all the QAs, who needs them? And we're all going to write tiny 100-line services that a bit like cells in the body will replace them every so often. So I tend to think of Fred's version as extreme SOA. It's kind of SOA, and I've turned the dials up to 11 for the Spinal Tap fans. But otherwise, you can just think of it around an ascent. And the reason that's useful to us is because much of the literature about SOA is still relevant in the world of microservices. So a couple of things to understand here. The first is basically what could we think of as a typical rules about a microservice. And this is where we get the 4 tenets, which you can see above. So one of them is that boundaries are explicit. What do we mean by that? Well, we mean that the only way to interact with our service is through a well-defined API. That could be an HTTP API, it could be gRPC, it could be events over AMQP. That we're not worrying about the technology choice that we're using, but what we're saying is there should be a well-defined API, which is hopefully stable. So when we basically partition our system into microservices, we seek stable boundaries, things that won't change too much over time, and that's why there's often alignment with the business's goals, business capabilities, sometimes it's called. Okay. Nothing else can peer inside that boundary. It's like the event horizon on a black hole. Okay. What is inside belongs to the owners of that microservice, the team that's building it. They can change the code as much as they want. They can change from using SQL Server to DynamoDB if they want. It shouldn't matter to anybody else. How they implement their service is entirely up to them, provided they maintain that contract. That contract is a dependency you can take. Anything inside is off limits. We also say that services are autonomous. What we mean by that is I should be able to release my microservice and have no impact on other services, provided I don't change my boundary contract. The boundary contract remains the same, I can release the whole thing. That means I can't share database tables. I A, violate my boundaries, and B, I'm no longer autonomous, because if you release me, how do I know I haven't broken somebody else who was reading from those tables directly? So you can't peer beyond this boundary that we've established around our microservice. A couple of other ones that are useful, but not so relevant to the talk. We share schema, not type. In other words, we don't use .NET assemblies between 2 microservices as a way of communicating what's going to appear on a wire. We use a format like JSON or XML or protobuf, whatever is appropriate. And that allows us actually to not care how the other microservice is implemented. I don't care how it's implemented. I just care it has a contract, right? The other team could be writing it in Lua, for all I care, as long as they provide the contract and they provide a decent SLA. And if you work in larger organizations, it's inevitable that you will eventually acquire a state of a larger number of frameworks and languages. And compatibility by policy is probably the least significant. Most of the time, that really says, in order for me to make a call to you, we're going to have to agree certain things like how we're doing authorization, and we'll have a policy-based approach to that. So we'll agree we're all going to use OAuth or whatever. Okay. But one of the things to understand is that even though I suggest that this is kind of a black hole, all my details live inside, data has to leave my microservice, otherwise it's not useful. Data leaves via that stable boundary. So you might, for example, issue a GET request. Can I have some data from your microservice, please? So we're going to use an example of hotel booking. I know nothing about hotel booking. If you work in hotel software, I apologize from the bottom of my heart for trashing your domain. But it's useful because you know my CV includes nothing in hotels, so you know I'm not talking about anything real. I may raise events from my microservice, right? I raise an event that says, this interesting thing happened in my microservice. Would you like to know about it? And there are a couple of interesting properties to those things that we raise from our boundary. So we don't own that data. There's a single writer of that data, and it is the microservice, and that writes the data inside. So we have no authority over it. It's just basically a copy that floats outside. Okay. It's immutable. There's no point in you changing that data. It won't cause an update to the data in the database contained inside the microservice. It is stale. As soon as the data leaves my boundary, it is possibly incorrect. If you can imagine that someone does a post into my booking service to create a new booking, when you go and get the list of bookings, if that post comes in seconds after you've got the list of bookings, your list of bookings is now stale. You don't have the information about that new booking that just arrived after you took the get bookings list. That's one of the reasons with things like HTTP, we will do things like put, for example, a cache control header on the information. We will say, how long do I think it's safe for you to hold on to this information inside a cache? You can keep a copy, but it's going to get stale. It's also a reason, for example, we have something like a last modified or an e-tag on an HTTP header. We say, I'm going to give you a way to determine whether the data you hold is still accurate. And so I can make an if modified since on my GET request and say, I've got a copy locally in my cache. Is it still any good? Or do I need to get a new version? And so essentially we version the data because it is stale to determine how current our data is. Oops. And Pat calls these two ideas of data outside data, data that lives outside our service. We authored it. You can have a copy of it. You can cache it. You can work with it and do whatever you will with it. And inside data, data that essentially belongs inside our microservice. Okay. And obviously the two have a relationship. But from the point of view of people outside, they don't know what that relationship is. Our inside data may look very much like our outside data, but it might look entirely different. Okay. Park that piece of information in your mind. We will come back to it. Let's talk a little bit about request versus architectures versus event-driven architectures and why you might favor an event-driven architecture. So I'm going to go light on the detail. There are a lot of things going on, but I'm going to try and highlight a particular issue. Let us imagine that when I get a direct booking into my company, I decide that essentially what I'm going to do is take a credit card payment, inform housekeeping that there is a booking on a given day, and go to my channel manager. So that's covering things like Expedia, bookings.com, all the places where I advertise my hotel, and tell them to decrement the availability of rooms for that given date. One of the problems, if what I'm doing here is making a call via HTTP plus JSON or gRPC, is that I need all of those services to be running in order to complete my booking. You can think of this like a phone call, right? I know we don't make phone calls anymore. My mum phones me, but everyone else would just send texts, right? But back in the day of phone calls, if I phone you up and you're not there, I'm kind of frustrated because I can't complete whatever action it is that I wanted to look at. And so if the channel manager is down, for example, my problem now is I may not be able to complete my booking because I've coupled my booking to the channel manager. Now, obviously, there are some workarounds. I could choose to ignore the fact that basically I failed to talk to channel manager and allow that situation to continue. But it's a particular property of request-driven architectures that you bind your uptime to the uptime of all the services you're dependent on. If all of your services have 99.9 uptime and you have about 4 of them, that gives you 99.5 uptime at best. That's an outage every day on average of about 10 minutes. Now you may say, 10 minutes. But I work for currently for a food provider called Just Eat. We connect consumers with restaurants and delivery partners. And 10 minutes during peak order is a lot of orders, hundreds of thousands of orders that we haven't taken and delivered to our restaurant partners. So although 10 minutes doesn't seem very much, it's at the wrong time of day. It's an enormously long window to fail for. So the question is, can we try and avoid these problems of request-driven architecture? Now, just as an aside, if you are forced into this model, that's where you get into load balancing across various instances, using a service mesh, et cetera, to try and give you retries and circuit breakers. So there are solutions. But one solution is basically to move to an event-driven architecture. So with an event-driven architecture, I simply raise an event that says, I have a direct booking. And I have all the other microservices simply subscribe to a channel, which is identified by a topic or a routing key that says, I want to hear about new direct bookings. Thanks very much, that'd be really great. And so, for example, housekeeping just says, I'm going to listen to direct bookings, and we send it a message. Now, the thing is, this is asynchronous and decoupled. It's like, because we don't send phone calls anymore, I send you an SMS, right? I send you an SMS, and you can retrieve it in 5 minutes when you finally get to look at your phone when you finish that important conversation that you were having about what you learned at NDC Oslo today. And that asynchronous property means it doesn't really matter to me if that other service is not available at that time. What it will do is just stick them in a queue. We refer to this as guaranteed delivery. Okay, channel manager will eventually get that message. Now, there is an issue called eventual consistency, and that means if channel manager is offline and then comes back online again, there is a window during which our availability will look greater than it is out there to basically customers using our service on booking.com or Expedia. Okay? And that is potentially a problem, but businesses solved that problem for many years before we had software. And so the usual model is a hotel will simply direct that booking to an overflow hotel where essentially it can be dealt with. But essentially you've got time as well. You could contact the customer and say, I'm sorry, we have to be fully booked on that date, and I'm afraid I'm going to have to cancel your booking. Okay? And here's a voucher for your next booking or whatever, or more reward points, or some mechanism that usually the business will understand to solve that problem. Okay. As an interesting aside, I had a situation where I arrived at a hotel where, from eventual consistency reasons, my housekeeping had not rented the room in time. It was a very expensive hotel, and they simply said to me, sir, go to the bar, and drink as much expensive alcohol as you like, and we'll tell you when your room is ready. And I was quite glad my room wasn't ready for quite some time, and I was quite drunk at that point, right? So there's always usually an adequate business solution to the problem of eventual consistency. Okay. But there's a question that usually comes up at this point. So I go away and I'm very excited. I'm going to build event-driven architectures. Ian's told me all about them. I've got my copy of NService Bus or Brighter or whatever. Off I go. And I building my system and I say, great, we're going to take a direct booking. And direct booking for a customer on account. And the customer with the account, his credit card details aren't part of the booking. We go and look them up against the credit card that we've got stored on file for the customer. How are we going to look up his account details? Because if my answer is that I request that information from the accounts microservice, I've just reintroduced temporal coupling into my workflow. Now, in principle, in this kind of scenario, I could retry a few times, maybe because accounts has got my message. Essentially, I think to myself, it's fine, I'll just keep retrying. But any flow where effectively you want to complete within a reasonable time window, this could be a significant problem, right? If accounts is down, how do I finish this operation in a way that essentially is going to allow me to release the resources I'm currently using in the credit card payment system, which are trying to get hold of information out of accounts? All right. So, what we're going to do is try and solve that problem in an event-driven way, rather than resorting back to using requests. So there are a couple of options, really. So if we look in the lower left-hand corner of that slide, what we could always do is ensure that the message that is received by the credit card payment service has all of the data it needs to process the request. So I simply make sure that from somewhere I have obtained your credit card details and added them into the request such that you can process it correctly. All right? And we're going to explain in a second what your options are for filling that data in on that message, assuming that it's not in the direct booking. So if the customer had a direct booking, not an account, and they've probably filled in their credit card and may have it right from the beginning of the process, but assuming in this slightly contrived scenario that I have to get the information out of the from your account details, how do I add that to the message, given that the direct booking event was raised by the direct bookings microservice, not by the accounts microservice? Okay. And the second option, which we'll get to after that, is that my payment service has the information it needs in a cache. It is cached information from the account service about accounts and their credit card details that it needs to service its requests. Okay? And the clue to what we're going to do is to think back to that early section about reference data. Right? Remember, we can cache data coming out of a service. Okay. So, messaging tends to work by a pipes and filters model. I have a source of a message. I have some endpoint destination, which I want to get to service the request. But I can insert an arbitrary number of steps between the two. And I simply publish to one channel, pick up the request, and then I essentially consume from another channel. And it's important usually, so by channel we mean something like a topic or a routing key, depending on your technology of choice. It's important to understand that you have multiple channels involved. So my direct bookings publishes something like direct booking made on account. Right? And the account service listens for those messages and it says, there's a direct booking made on account. I need to enrich that message with the credit card information. When I've added the credit card information, I will raise a message which is something like direct booking made with credit card details. And the credit card payment system listens to that message and says, great, I've got a direct booking and I've got the credit card details. I can take the payment. So by using that pipeline, we are able to leave microservices as the single authorities about their own data. I don't have to let you call me to get hold of that data via a request, or even worse, reach in beyond my boundary to my database. I simply ask you to complete a pipeline where you will enrich the data before it reaches me. Now, you can have a little bit of concern about the latency. I'm making some extra hops. Maybe if I need something highly performant, this is not the better option. I'll come back to other options in a second. Sometimes that model gets quite complicated. So the previous way of doing it, where essentially I just create a pipeline and I pass events between one and the other, we tend to refer to as choreography. I am simply letting events flow around the system, and I listen to this event, you publish that event, etc. Okay? Another model is called orchestration, and orchestration says a component, an orchestrator, usually thought of logically as being at the API gateway layer, conducts the flow of operations. So it says, I want to make a direct booking, and the direct booking system says, okay, great. I've raised a direct booking in the direct booking system. And the Saga then says, okay, great. I need to fill in the account details because basically the type of booking was a booking on account. Hey, account system, fill in the account details on this message. Then it passes it to the credit card system and says, hey, credit card system, here is a message basically for a direct booking for this account. Go and take the payment. Now, in a trivial example like this, there's probably no significant advantage over the first flow. But the real advantage of this process is I can add compensation. So compensation is what I do when something goes wrong, right? What do I do when your credit card is declined? Now, you can actually, in this particular case, solve the problem by choreography if you want to as well. So I just had a situation where my credit card had passed over its expiry date for a booking I'd made in a hotel probably 9 months ago. And actually all that happened was they just phoned me up and they said, Mr. Cooper, could you give us a new credit card? And that's called manual compensation, right? Effectively, and that's quite possible. By choreography, we have a booking status and something that goes to the bookings every so often and says, are there any bookings that basically have a status of effectively, card declined or whatever? But with this process of a Saga, I can manage that in some way, right? The Saga can effectively update my direct booking and say, change your status to card declined. It may send an email to an operator saying, please contact Mr. Cooper and tell him his card has been declined and he needs to replace it with a new one, etc. And I can control that flow. And it also gives me a central point, usually because it's storing state in some kind of database, generally a Saga state machine, and it's storing a database, saying, so I can go and query that and say, where is Mr. Cooper's booking? And that's useful if someone gets on the phone to a call center and say, because I've just complained saying, I made a booking at your hotel on the 15th and I've received no confirmation. Someone can go in, look at the state of that particular transaction, and it says to them, Mr. Cooper's card was declined. And they can then say to me, your card was declined, Mr. Cooper, would you like to present a new card? Right? So having some kind of Saga helps manage that process. Okay. But earlier on, we talked about this model, right? We said that Pat Helland had defined that there was outside data and inside data. And the outside data is what comes out of a microservice in the form of data we get via basically an HTTP request or a gRPC request, or events that we raise from the boundary of the system. And that data is immutable, stale, and versioned, and it is very suitable for caching. So what I could do is listen to events being raised by the accounts system. And the account system would publish events when a new account was created or it was updated. And maybe it raises quite specific events like credit card details updated, so I only have to listen for a fraction of the events coming out of the account system, ones that I know I'm interested in. And what that lets me do is build a cache of the account system's data that I, as the payment service, own and can access. It lives within my boundary. It's my copy. I may only use a small number of fields that the account system actually creates when it publishes. For example, the credit card number, the CVC code, maybe some of your address details so that I can confirm those. But I can listen to the account system and construct a cache which I can then use at runtime to service my requests. So account set is something like, credit card details updated, a worker process running inside my microservice updates my local cache of account data. And I just sit there listening to events from accounts, updating my own version of what lives in the account system. And then when a booking event is raised, I can simply ask my local cache about your credit card details rather than making a request back to you. And the significant advantage of this model is that I am essentially now insulated from your system and its uptime and availability. Because I can service requests without accounts being available. You can't add a new account and you can't update your credit card details if accounts is down. But from the flow of me taking new hotel bookings, that's viable. And seeing as that's probably my money-making flow, that's one I want to protect against the loss of availability of a service. So while accounts, I may not care if accounts is down for a window of time, I might put up a window saying, sorry, it's not possible to add a new account at this point in time. Certainly with my booking flow, I want to make sure there's no real impediment. And if you're booking on account, right, telling you to come back later is probably going to cost, you're just going to go somewhere else. But with a model like this, I'm insulated from your system. I have no dependencies, right? I receive the event and I'm able to act on it on my own. And in turn, credit card payments, after it's essentially made the payment, will raise its own events. And that can be listened to by systems downstream from credit card payments, which may in turn be using the data for their own purposes. For example, maybe raising financial information, accounts, invoices, reports, right? I don't care who they are. They can have a cache of my data as well. They don't own that data, right? It's potentially stale. They should track version numbers against it. But that data essentially is usable by them to process requests. Okay. The process of using events to create reference data, I'm going to show you that again, is called event-carried state transfer. Martin Fowler named it recently. We've been doing it for years, but Martin's now named it, so that's great. We can all talk about it. It exists now. Does anything in technology exist until Martin names it? I'm not really sure. But yeah, earlier on, people quite often referred to it by just the term reference data. And one of the interesting things I noted over time about reference data is that, for example, if you read the book Rest in Practice, they refer to reference data, but they don't explain it. They just assume that you understand what it is. It's like kind of one of the great secrets of architecture and building event-driven architectures. They see thing called reference data. People say, oh, and if you're building reference data, you should do this. And people are like, what is reference data, right? So you may see the term reference data. You may see the term projections, because people often liken this to a CQRS model where effectively I have commands coming into a system and I'm generating a view off that basically from what happens there. And you make people relate it as well to some of the ideas in event sourcing where effectively you are building a projection off a stream of events. So there are related ideas. If you really want to cause a fight on Twitter because you're bored one afternoon, you simply say something like on Twitter, hey, I'm really interested in using Kafka for event sourcing. This will cause a fight. Really, most of the scenarios that the Kafka, people like Confluent are describing for Kafka are actually event-carried state transfer, not event sourcing. But it upsets people. It's fun to get the popcorn and stand back and watch, basically, as the blood congeals on the floor. Okay. So reference data's been around for a while. So event-carried state transfer is one approach to doing it. But there are others. Atom feeds. So you may see this one talked about. Vaughan Vernon, who's here somewhere at this conference, I think in one of his domain-driven design books, talks about this model. So at one point, people would say, I'm going to use an atom feed to expose all of the events that have happened inside my microservice. And they use an atom fee because it has some interesting properties. And then one of those is that every page after the current page is immutable. It will always have the same contents. And that makes it very easy for you to read an event history. Because I start on the current page and I just keep paging until I see the first event that I recognize. Then I go back to the beginning. And they use a lot of e-tags to tell you whether the page has changed. So I can query the current page and say, are there new entries on this page? So I can poll that and only read in that case. So it's a quite efficient mechanism. Nowadays, because there are better technology choices available, it's used less than it was in the past. But it's a very easy to access version if you have trouble installing middleware, etc., in your organization. Extract, transform, and load. So people have done this a lot in the past by simply replicating data out of a database in one SOA into another SOA, right? Lots of banks in London for years have used this approach of replicating their data everywhere by using ETL. It's a valid strategy. The problem, of course, is ETL is not always the best, particularly if you're doing things like using transaction logs for other systems. But also you're binding yourself to using the same database technology usually across all your microservices. And that may not be what you want to do. One microservice might want to use a GraphDB, one might want to use basically Dynamo or Cosmos. And so that kind of binding, you're removed from that dependency on technology by using essentially events as the medium effectively to transmit over. You can use FTP as well, right? And a perfectly valid strategy. Although the more modern equivalent would be write something to blob storage somewhere effectively and read from that instead. And essentially you're doing pretty much what some of the message log providers, which we'll talk about in a second, do by creating effectively an append-only stream of events. Okay. So various strategies you can use. I do a lot of ECST, but then I'm kind of an events guy. But you can pick other ones if you want to. Okay. There are various types of reference data you can share. Operand data. Operand data is essentially useful when you want something like a product description, right? Or some of those tiny, I've got an ID, I want to have the description, so I can return the description in you make a GET request to me, I've just got an ID about a product in another system, rather than effectively having to mix GET recalls to both systems, so I can just fill in the description, I can have it in my reference data, and I can just include that in the return value. Shared collections. So shared collections are mostly what this is used for. And so we say these are lists of things that nearly every microservice in your system needs. So lists of customers or users of the system. Lists of companies basically registered to use your platform. So Just Eat, for example, have things like lists of restaurants, lists of customers, lists of delivery partners. Okay? Because most of your microservices will need that data in some way to operate, and it saves you continually making request-based calls to those other architectures, right? Just think about it this way, if you're slightly dubious. If I was going to make an HTTP request to get that data, then the HTTP request would surely indicate to me that I could cache it, because HTTP, that's how the web scales, we cache data. And you cache locally. You cache basically at the point of the consumer, not in the origin server. So what I'm doing is caching the HTTP request data. But if I do event carriage state transfer, I'm just doing it off an event. And I read that local cache, rather than asking you again for the same data. And historic artifacts. Historic artifacts are less useful in your transactional system. That tends to be more, I am filling my data lake full of stuff based on the events that I had in the microservices. Because it turns out that now I put all my data into individual microservices, it's really difficult to create queries that cross multiple microservice boundaries. So I'm going to take all that event data and I'm going to shove it into a massive lake where effectively I can then query it. My biggest tip is that reference data should not know the rules. What do I mean by that? When I receive an event or make a GET request to you, I interpret the data you give me myself by my own rules. What I don't do is copy your rules from inside your microservice and then apply them to my service. Because then I've coupled domain knowledge between these two microservices. And if it changes in one, it's going to have to change in the other. Okay. So you need to be able to interpret that yourself. Don't replicate the rules. And if the data in the other microservice has to be understood by complex algorithms, for example, we have some stuff at Just Eat about delivery radiuses, etc., and where we'll deliver to and what time windows are about that. It's not a suitable artifact for reference data. You're better off using that kind of pipeline approach and doing choreography or orchestration to fill the data in that context. You're going to get more latency, because the great thing about reference data is it's pretty low latency. You're just calling a database, right? It's faster than making that request over an architecture was in the first place. And it's certainly faster than basically filling that pipeline of the messages it flows through choreography or orchestration. Okay. So don't pick reference data where essentially you need to bring the rules with you. Most of it should be fairly basic stuff. But for example, credit card details, the account system has no rules about it. It's the credit card payment system that's going to have the rules about it. Correctness. Okay. This is the hard part. So I'm going to just drink some water. Oh, my battery's low. Hang on. All right. So if I am sending data from, say, my account system, and it's being picked up by the credit card microservice downstream, I want to make sure that they both agree on what the current state of the account is, what the credit card information that you put on file is. It's no good me trying to take a payment from a historical credit card and then saying it's declined, and you phoning up the customer and the customer saying, but I gave you the new credit card details yesterday. You might get away with latency of a short window. The customer's probably going to tolerate that. But yesterday's going to be no good. So I need to make sure that the changes in the account system always flow to the downstream credit card payment system. Okay, so in this particular, in fact it says order service, particular model, right? The service essentially that effectively wants to change its own state, the order service, is going to write to the orders table. Ignore the outbox for the moment. And it's also going to write to the message broker to send a message downstream to say, hey, I have changed the state basically of this given record. So we'll just use the example of accounts. We'll say it's account service and send it out to the message broker. It's unlikely that we can create a transaction across our message broker and our database. Probably the two technologies don't share any kind of distributed transaction coordinator. Maybe if we're using MSMQ and we're using SQL Server, that will work. But essentially, even then, we introduce a scaling issue that by basically holding a transaction open across two resources, everything will slow down. But that creates a risk. There's a risk, for example, that I might write to my database and update it and say, here are the new credit card details. But when I try and send it to the message broker, I fail. It's down for whatever reason. Okay? And in theory, there's also a risk which kind of says, I could sort of swap that around. I could say, well, I'll solve that problem. I'll send to my message broker, and only if I succeed at sending my message broker will I update the table. That creates the reverse problem. I may now have told the downstream account system that the credit card has changed, but not the upstream account system, and that may cause problems in the future for me. So to fix that problem, there's a pattern called the outbox. And the outbox says what I do is I create a table, and I write in a transaction to the accounts table that has my credit card information, and the outbox table, and I put the message I want to send into the outbox table. And typically, if I'm using a relational data store, I have some header properties that say things here like, here are the header properties of the message, and a field which is just some JSON or whatever that has the body of the message stored inside it. Okay. And then I send the message knowing that I've safely got that message in the outbox. Now, I have two strategies. Strategy one, which is kind of my preference, says I put it in the outbox and then I just send the message as normal. Right. Strategy 2 says I send the message directly from I read the outbox table and send the message from the outbox. Okay. I prefer the first strategy because otherwise I'm tending to use the outbox table as a queue, which means I have to do some interesting SQL to get that to work right. Okay. Now, if I fail to send to the broker, what I can do is have another process, another worker process running in the background that says, okay, when did you write to the outbox table? Have I seen, is there a timestamp saying it was sent via the message broker? Because when the broker sends it, it updates the outbox table in the message, and it says, with a timestamp, I've sent the message at this time point. Okay. If I don't see one of those, I know that I should resend it. So this worker process spinning in the background says, are there any messages older than 5 minutes that don't have a timestamp? I'm going to resend those. Now, there's a risk, and the risk is that when I write to the message broker and try and update the outbox table, I fail because the database is not available, right? That's okay. I just send the message downstream anyway. The downstream system has to basically deal with duplicates. That's what we tend to refer to guaranteed at least once delivery, because I may send you the message more than once. Okay? So I send the message downstream so I can guarantee that you will eventually receive any of the updates made to the outbox table. Now, there can be an issue here, and the issue is that essentially some databases, for example, MongoDB, are not going to support a transaction across an accounts document and an outbox document. So what can I do? Okay. Oh. So there's another option we can use called log tailing if your database supports it. And log tailing says I am going to listen to the transaction log on the database and use that to generate my events. Okay. So DynamoDB, for example, on AWS supports this. I can just listen to its log. As the log generates events, I say, okay, that transaction log is effectively what I'm going to use for my outbox, and I will effectively listen to those events, and I will raise events and send them on the broker downstream. And DynamoDB replication itself is actually done by effectively listening to the transaction log, pushing events over Kinesis, and then reading them on the other DynamoDB instance and updating the table effectively in the DynamoDB instance. The DynamoDB does this as its method of replicating between two systems. If neither of those work, my third option is I write to the broker. And when I've succeeded at writing to the broker, I listen to the message that I've just written to the broker and update my own state. So in this equation, both sides listen to the broker to update state, both the data source and the data sink. Okay. Now, there's obviously a slight downside with this, and that is that essentially timing issues can mean that the downstream system knows about something before the upstream system does, and you get things like the customer get a notification that their credit card has been debited for a certain amount, and you haven't even confirmed their order to them. But usually these things catch up, right? And customers are often tolerant to that kind of problem. But it is a little bit of a funky one because people are sometimes a bit like, I don't write my own local state, I just listen to the queue. Okay. Logs versus queues. You can also have this discussion, we could call it RabbitMQ versus Kafka, if you like. Right. So things like RabbitMQ have a model we call a shared queue. What do we mean by shared queue? I mean that when I send you a message downstream and you pull it off and update your account's reference data, we delete the message off the queue. So it's gone. Okay? I keep eating messages off the queue. I can tell where I am because the head of the queue is the next thing to process. Okay. But what happens if I introduce a new service into my environment? It particularly happens in non-production environments like QA. Someone releases a new version of their service. I need to build my cache. My cache is empty. I don't have any credit card data. How am I going to fill it? So the answer in this model is that hopefully I have an outbox and I resend the messages out of the outbox saying, here's all the things that happened in accounts. And the problem with this model, though, is that everybody now gets a notification of all the things that happened in accounts. And they have to have some kind of, hopefully, an inbox where they deduplicate, where they say, discard it, I've seen it. Discard it, I've seen it. Discard it, I've seen it, right? And that creates quite a lot of work, to be frank, for all the systems basically in all the parts of your system just to onboard this one new microservice and populate its cache, or because you want to blow the cache away for whatever reason and start again. Okay. So the advantage that message log systems like Kafka or Kinesis, and I think it's Streams in Azure, I'm not an Azure person, have, is that I don't delete. What I do is I advance the index pointer, but the data remains essentially because it's written to disk. And I can reset the index pointer back to 0, or a new service can start at 0 and consume all the events. It's a bit like that atom feed we were talking about earlier. Okay? New service points towards the accounts feed. I read nothing so far. I'm at 0. I just go reading all the way through. Service has been around for age, maybe record 40,000 or whatever, right? Generally speaking, to do this, though, you have to rely on the ability to store that data forever, or at least do some kind of snapshots to let you truncate the data at some point so that you can start from a given origin. Okay. Kafka has a thing called infinite retention, which really helps with this. You can look at other models, for example, like saving snapshots out to S3 as a starting point for your data. Okay. Generally, my experience has been that message log style technologies are easier once you get this working to deliver event carriage state transfer. And indeed, if you talk to people like Confluent, they see the event carriage state transfer model as being one of the key successful scenarios where you can deploy message log-based technologies over shared queue technologies, right? There are various trade-offs between the two technology choices, but this is definitely one of their sweet spots where they work very well. And it's this stuff that tends to cause the argument with the event sourcing people. And outbox and inbox don't tend to be needed so much in message logs because the message log itself is the outbox and the inbox, effectively. And there are even technologies for Java, for example, called Streams, which, although I've never tried it, in theory we suspect may be usable to build actual reference data by pointing at the stream of data without having to do it directly. But it's not something I've really played with. Okay. So a couple of things to touch on just at the end, which kind of relate to this piece, and just to try and give you the full picture. So this has mostly been talking about what happens in event-driven systems when I want to, in microservices, when I want to basically handle the workflow from some kind of request coming in to do some work, a task has reached me, right? And what happens in microservices when I want to get data? So typically, you essentially have a model of composition either by the client or, we're going to show the next slide, the server, right? So the client simply says, there's an accounts microservice, a credit card payments, a direct booking service. I'll just talk to all of them. And if I need data, I'll just get the data from all of them. They're outside the perimeter, and it's very difficult for them to talk to any kind of event model. So you have to rely basically on good old request-driven architectures. So you can do that at the client, or effectively you can do it at the server, where you form part of the gateway. The main reason for doing it at the server is simply you reduce the latency, right? Rather than making that call effectively from your mobile phone to get across to 12 APIs to get the service, I just basically make one call to your software effectively, and it makes the calls internally to those 12 services, basically. And then you can also do lots of management there because it's a request-driven operation around retries, circuit breakers, all that stuff that, say, Hystrix pioneered that now we get in service meshes. And the other model, though, that's kind of more interesting for this discussion is that I can build what's sometimes called a composite view model. And that says, if what I want to do is take data from a number of services and build something that's just a simple kind of select statement that just says, give me a row or give me 4 or 5 rows of pre-calculated information, then I can actually just listen to events and build a read-only projection from basically that reference data that you can then query. And this is effectively this idea of historical artifacts. Okay. And it's particularly useful if you can avoid calling a microservice to calculate something. You can just say, I can calculate ahead of time what this result will look like. So when the user queries, it's just simply a low latency call into a database to get their data back. Okay. And that saves you from this world of having to call multiple APIs to do composition. You're simply querying a pre-built cache that looks like the results of their query. All right, so this basically our lovely and a bit of animation, and we're building up our view. Okay. And typically it is used for things like order history, things like that. That's where the customer wants to see something that ranges across a range of data. Okay. In theory, although that's really kind of outside the scope of the topic of this talk, you're doing exactly the same thing when you build a data lake, right? Your data lake is simply really just listening to all the events that happen in your various microservices, collecting the data, and putting it together in some big store that you can then go later and effectively create queries against. All right. Oh, one more to go. I was getting excessive there. Okay, and with that we are done. There's a couple of minutes for questions, I suspect. If anyone wants to ask a question, I can see you. You can always come and grab me. I'm iCooper on Twitter. My DMs are open, so you can just direct message me, and I'm happy to talk about this stuff ad nauseum. But otherwise, we are done. And please don't forget to vote for me. Green tickets are votes.